Okay, so we're going to get started here with some problems. Okay, so we're working in chapter 23, and basically there's two types of problems that you're going to see in this chapter. You're going to see a simple circuit analysis using series and parallel circuits, or you're going to see Kirchhoff's laws. One or the other is going to be what the problem is going to be about. So we're going to start out with a simple circuit reduction problem, kind of like I showed in the videos that I've posted. But we're going to start looking at problem 10. Okay, so this is going to be problem 10. All right, in problem 10, you've got an A part and a B part. And so in A part, you've got some resistors that look like so. Like that. There's your resistors. And this one is 2 ohms. And this one is 3 ohms. And this one is 6 ohms. Okay. And the question is to find the equivalent resistance of each group of resistors shown. So the first thing I have to do is figure out what type of series or circuit this is. Now I notice if I had current flow through here, say the current flow started here and it needed to get to here, there's only one path that it can take. And since there's only one path that it can take, that means it's a series circuit. Okay. And even though this is not part of the problem, there are some things I know about series circuits. And what I know about series circuits is in every element, the current is the same. So the total current through the whole piece of the circuit or the whole circuit is the same as the current through each individual element. Okay, so in series, that's what's true. Then I know that the voltages add up. So each element may have a different voltage because it could have a different resistance, but they have to add up to the total voltage. Okay, now these don't have anything to do with the problem that this asks about, but these are good things to kind of exercise your mind and remember that that's the case. Okay, so I want to solve this problem. So I know that our total for series is I literally just add up how many ever resistors that I have. Okay, I add them up and very straightforward like that. So I literally just add them. So it's going to be 2 ohms plus 3 ohms plus 6 ohms, which is just 11 ohms. Now, the thing to remember in series is your total resistance is going to be larger than your largest resistance. Okay, so my largest resistance here was 6. I'm adding something to 6, so my total resistance is going to be larger than 6. So it's going to be 11 ohms. Okay. All right. Now the second picture has a slightly different drawing. Okay, so this was A part. Okay, B part, you've got this. Now, when I look at this, it looks different than A part, but the question you have to ask yourself is, how many paths do I have for the current to flow through here? So if I go back and I look at the current, if I had current coming in here and it needed to get to here, you know, if I have current coming in one side and it needs to get to the other side, there's only one way for it to flow through these resistors. So even though these look strange, these are still series. There's only one path for the current to flow through. Okay. So since it's still a series resistance, I just do like I did in the first part. I just add them up. So this one's just going to be 3 ohms plus 3 ohms plus 3 ohms. That's it. So that's going to be 9 ohms. So the point of this problem is to show you that just because it's shaped in a different way, this one, the part B one, is shaped like a half of a box or something like that. That's still a series circuit because there's only one path for the current to flow through. Okay. All right. So let's move on from that and let's look at a similar problem, but they're configured slightly differently. Let's look at problem 11. Now, problem 11 has got the same kind of idea. We're not going to do all 3 parts of problem 11, but we're going to look at it. It says find the equivalent resistance in each group of resistors shown in the figure. Okay, so if I draw the first group, okay, if I draw the first group, I've got something that looks like this. Something that looks kind of like that, all right? Now, when I look at this, what's going to happen here is the current is going to flow through, and if it starts here, when it comes in here, if it's trying to get to over here, well, it's got multiple paths it can take. So what's going to happen is part of the current can go here, part can go here, and part can go down here. And then they all come back together at this point. So what happens is I total will split up and go through these 3 different paths. Okay, it's kind of like when you go to the grocery store and you're trying to get to the front of the store and one of the aisles is blocked. So you go down and find another aisle. Okay, it's the same kind of idea. We call this configuration parallel because there's parallel paths for the current to flow along. Okay, in parallel, we know there's some differences here. If I were to put a battery across this and measure the voltage, because they're all basically connected on this end and on this end, the voltages are all the same. So in parallel, all the elements have the same voltage. Now that's true if the whole circuit's parallel or if the individual parts of the circuit are parallel. For that segment, the voltage is the same for all the elements. But because the current divides or splits up, the total current is an addition of all the currents. Okay, so again, this doesn't have anything to do with how to solve this problem, but it's just a good thing to remember for when you're working problems in the future. Okay, so for parallel, I know that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, they told me in this problem that this top one was 2 ohms, this middle one is 3 ohms, and this bottom one is 6 ohms, so kind of like what we had before. So I'm going to put those down here. So 1 over R total is equal to 1 over 2 plus 1 over 3 plus 1 over 6. Now, I know immediately you're probably going to try to pull your calculator out and work this out, and that's fine. But I like to use fractions to do these. Then I don't need a calculator usually. So I'm going to get a common denominator. So 1/2 is 3 over 6. 1/3 is 2 over 6. And then I've got 1 over 6. And I add those up. I get 6 over 6. So 1 over R total is 6 over 6. So I have to flip that over. And when I do that, I get 1 ohm because 6 over 6 is 1. And then but I have to remember, I have to take the reciprocal of this. So if these were 2 different numbers here, if these 2 numbers were different, then I would have to do the math and then take the reciprocal of it. In this case, they end up being 1, and 1 divided by 1 is still 1. Okay. So we're going to do another one, but I use fractions to do this because then I don't have to pull my calculator out and possibly type in something wrong and make a mistake. So I like to use common denominators on these. Okay, so we're going to do another one in this same problem set. Okay, we're going to look at part B. So part B has a similar picture. Okay, they're arranged a little bit differently, but that's okay. They come down like so. Like that, okay. And they want me to find the equivalent resistance. So each one of these is 3 ohms. Oops. Each one of these is 3 ohms. Okay, now, this is still parallel. And I know this because if current flow comes in, say from the top, it's going to split and go down each one of these three paths. So this is still parallel. Okay. Oops. Okay. It's hard to write on one of these things when you're left-handed. All right. So I'm still going to use the same. I'm still going to use the same formula that I used before. I'm going to use 1 over R total. Okay. Now, so I've got my 3. I'm going to do the same thing as I did before. Put in my numbers. So it's 1 over 3 plus 1 over 3 plus 1 over 3. Now here, I do have a common denominator, so I can just add those up, and that's 3 over 3. So that's going to be 1 again. So our total, I have to take the reciprocal, but the reciprocal of 1 is still 1. It's just 1 ohm. Okay. Now in parallel, your resistance is always going to be smaller than your smallest resistance. Okay. So yeah, so I have to split those up like so. All right. So now, so that's how you do series and parallel in a simple circuit, but they can look more complicated than that. So let's look at a problem that's not as straightforward. What you have to do if you have a more complex circuit is you have to break it down piece by piece. So it may take 2 or 3 or 4 or more steps depending on how complicated your circuit is. Okay, so let's look at a more complicated problem. Okay, so if I want to look at, say, problem number 19. Okay, or yeah, 19. So you've got, if you look at the figures for, if you've got your book and you look at the figures for number 19, let's start with the figure on the right. Okay, so it says here, what is the equivalent resistance between points A and B? So we're going to start with the figure on the right. So I'm going to draw that real quick. Like that, and then that, and then A is up here, and B is down here. And then this one is 10 ohms, and then this one is 30, and this one is 60, and this one is 10. Okay, and I'm going to label these R1, R2, R3, and R4, just so I can keep up with them, do my bookkeeping to keep up with them. Okay, so the first thing I have to do is I can't use just plain series or just plain parallel on these because I've got things that are blocking, like for example, okay, this branch is in parallel with this branch, but the problem is there's 2 resistors there. Okay, so I can't just immediately go straight to parallel. Okay, so I have to do something else first. Okay, so what I'm going to do is I'm going to look for a segment of this picture that I can just isolate and say, okay, that just by itself is either series or it's parallel. And what I see is if I put a circle around this part right here, those 2 are in series. So R1 and R2 are in series with each other. Now I'm gonna learn to write on this thing where I don't look like I'm 5. All right, so I can take those and break them down first. So let me do that first. So I've got R12 is just equal to R1 plus R2. Okay. All right. So because they're just in series with each other. So if I add those two together, and I'm not going to bother writing out my work, but one of them's 10 and one of them's 30. So the total there is 40. Okay. So what that means is I can replace that circled segment with a single resistor of 40 ohms, and that will be equivalent. So that's what I'm going to do. I'm going to redraw this picture, and I'm going to replace the two I have circled with a single resistor. So I'm kind of folding this circuit in on itself. Okay, so I'm just going to quickly redraw my picture to see what's going on now. So I can replace the two I have circled with 1. So now this is R12. This is R3. And this is R4. Okay. All right. Now the next thing I'm going to do is I'm going to look for, again, things that are just in parallel or just in series. So if I look at this section right here, these two are just in parallel with each other. Okay. There's nothing blocking them. There's nothing else in the way. So those two are just in parallel. So I can say that R12 and R3 are in parallel. Okay. All right. So that means I'm going to call it 1 over. Oops, let me write with my white marker here. All right. So it's 1 over R123 is equal to, now flare. Is equal to 1 over R12 plus, there we go, 1 over R3. Okay. All right. So I'm going to take my numbers for that. So I know that R12 is 40 because I solved that for part A, or the first part. And I know this one is 60. Okay. So I've got 1 over 40 plus 1 over 60. Okay. Now, because I like to do common denominator, my common denominator here is going to be 120 because they'll both go into 120. All right. So well, so if I do that, no, it's not wanting to write for me here. Get out of this real quick and go back. All right. No. All right. So if I do that, then what I've got is, if it's not going to let me do this, go back. No, it froze up on me. It's lovely. Okay, hang on just a second, guys. Let me unfreeze. All right, so if I use 120 as my common denominator, then 40 goes into 123 times, and 60 goes into 123 2 times. So that's 5 over 120. Okay, so R123 then is 120 divided by 5. Because I have to take the reciprocal, remember. And then if I do that, I get what? 24? 24 ohms. Okay, so then what that means is I can replace this circled piece up here with a single resistor of 24 ohms. Okay, so let me redraw this one more time. So what I do when I'm working these problems is I kind of go through and I redraw as I go and simplify. So I'm going to redraw as I go. So I'm going to replace this, and this is going to be R123 now. And then I have R4 down here. This one is 24 ohms. And then this one is 10 ohms. And so now I'm down to my last piece. And so now I've got these two. They're clearly in series. So R123 and R4 are in series. Okay. So then I just add them up. So now I'm done all the way down. So it's just our total is R123 plus R4. One's 24 and one's 10. So the total resistance of this whole configuration is 34 ohms. So what that means is I can replace all of those resistors with one. Oops, one. Oh, that's terrible. Let me draw that again. Okay, with one that's 34 ohms, and they'll draw the same current out of the battery, and it'll have the same voltage drop across it as that whole combination. Okay, so when we're trying to find equivalent resistance, that's what we do. We just start with the most complex picture, and then we reduce it down step at a time. So we went from R1 and 2 in series, we went down to it. You know, we started here, we went down to this and made R12. Then we took these two in parallel and we went down to this. And then once we got down to there, we reduced it down to that. So you just have to keep doing that until you get down to one resistor. All right. So you're either going to look for things that are in series combination or in parallel combination and just kind of fold them into each other. Now, why this matters is because now what I can do is I can use this to solve for the potential and the potential different, or excuse me, the potential across a resistor and the current through a resistor. So what I can do is I can use that to do something like problem 28. Okay. All right, so problem 28 says find the current through and the potential difference across each resistor in the figure. Okay, so we're going to draw our figure. So this is problem 28. All right, our starting figure looks something like this. And then I have a battery here. Okay, this is 10 volts. And if I don't remember, the long side is plus and the short side is minus. Okay, I'm going to call this one R1 and it's 5 ohms. I'm going to call this one R2 and it's also, oh, they're all 5 ohms. Okay, they're all 5 ohms. This one's R3 and then R4 is also, these are all 5 ohms in this case. Now, if I want to find the current, I need to find I total. Okay, and then that way I'll know how it splits up. So the way that I find I total is I need to find R total. I need to find the total resistance of the whole combination. Okay. All right, so I need to find the total resistance of the whole combination. And the way that I'm going to do that is I'm going to reduce this down to a single resistor. Because if I want to find I total, it's V total over R total. Now I know V total, it's 10 volts. So I need to find R total. Okay. So I've got to reduce this down. So I'm going to look at my picture and I'm going to look for the first grouping of resistors that I can put together that are either all in series or all in parallel. And if I do that, I see that this group right here, they're all in parallel together, right? So I'm going to reduce those down. So I'm going to say, I'm just going to call it R234 because that's what it is 1 over R2 plus 1 over R3 plus 1 over R4. So 1 over R234 is just 1 over 5 plus 1 over 5 plus 1 over 5. I don't even need to get a common denominator. That's 3 over 5. Okay. So R234 then is 5 over 3. And I have to do that math, but I can do that pretty easy. Okay. It's just 1.67 ohms. Okay. All right. So then that means I can replace the things that are circled in red with a single resistor equal to 1.67. So let me do that real quick. Looks like that. So this is R1, this is R234, and then this is still V. And we'll just call it V total. So now I see that all I've got left is these two, and they're in series. There's only one path for the current to flow. Even though there's a corner here, it's just a corner. There's no junction. The current can't go anywhere else. It has to turn the corner. So I've got now our total is just R1 plus R234. Okay, so that's just 5 ohms plus 1.67 ohms or 6.67 ohms. Okay, all right. So now I've got our total. So now I can find I total. Okay, so I total is just 10 volts divided by 6.67 ohms. Okay, and if I do that, I got basically 1.5 amps for my current. So this is I total. Now, this is where these drawings are going to come in handy because you know there's 1.5 amps coming out of the battery. So what that means is that 1.5 amps comes out of the battery and it goes through the circuit like this. So I can see right away, and the question says, what is the current through and the potential difference across each resistor? I can see right away that R1 gets all of the current because it is by itself. So R1, it has I total. Its I is equal to I total because it's in series with the whole thing or with the battery. So it's 1.5 amps. Then to find V1, I just use Ohm's law. V1 is equal to I1 times R1. So 1.5 amps times R1, which was 5 ohms. So that should just be 7.5. 7.5 volts. Okay, so I've got taken care of R1. I found the voltage across it. I found the current through it. Okay, now, so what that means is I know that right here, I've got 7.5 volts. Then I have to go back and remember, well, the rule is in series, the voltages add up. So if my total voltage is 10 and 7.5 of it goes to R1, that means there's 2.5 left to go through this other resistor. So that means I know for the equivalent resistance of R234, I've got a voltage across there that's whatever was left over from the 10 volts. So it's 2.5. Okay. But if I remember, that resistance is really 3 in parallel. And so since they're in parallel, remember, everything gets the same voltage. So if there's 2.5 volts across this whole thing here, then that means that each one of those individual resistors that go into making that up gets 2.5. So that means I know that V2 is 2.5 volts. I know V3 is 2.5 volts. And I know V4 is 2.5 volts because they all get the same resistance, or excuse me, the same voltage. Okay, because that's true for things in parallel. This is why it's helpful to redraw the pictures so that you can break it down. So if I go back and remember, that really is this thing here. Okay, it really is that. So if there's 2.5 volts across that whole thing, then each one of those gets 2.5 volts. Okay. All right. So now I want to find the current. So I'm going to go back to Ohm's law. So I2 is V2 over R2. So then that's just 2.5 volts over R2, which is 5 ohms. So that's just 0.5. Okay. All right. Then I'm going to do the same thing with I3, which is just V3 over R3, which is also going to be 0.5 if you do the math. So it's 0.5 amps. And I4 is going to be the same thing, V4 over R4. And that's also going to be 0.5 amps. Now, they happen to all be the same here because they're all the same value of resistance. If these were different values of resistance, these currents would be different. So don't assume it's always going to be the same. But I know if I go back to my picture up here, if 1.5 volts, or excuse me, 1.5 amps came through here, then that means 1.5 amps has to go through here. Okay. But it has to split up because that really is 3 resistors hiding inside there. So I know that my currents better add up to 1.5 amps, and they do. 0.5 plus 0.5 plus 0.5 is 1.5. So that tells me that I probably did my math right. So I'm done. I've got all the currents. I've got all the potential differences. So now I know what they all are. Okay. But it takes a little bit of practice to do this. So I really encourage you to go back and rework this problem and kind of practice on that. You know, get practice on getting used to figuring out how to fold these things down into a single resistance and then work your way back. So we'll practice that. The video, the extra video that I'm going to do, I'll do another one of those so that you can see that done again. But I want to move on to the other type of problem right now. And so we're going to go ahead and do a Kirchhoff's law problem for you to see. And then I'll do some more of those in the extra video that I'm going to do. All right. So Kirchhoff's laws are the loop rule and the junction rule. So remember, the loop rule said, oops, get rid of you. All right. The loop rule said that the total current, or excuse me, the total potential difference around a loop, if you start in the same place, is equal to 0. And then the total current and coming in and out of a junction has to equal 0. So this was the loop rule, and this was the junction rule. Okay. Now, what you do is with Kirchhoff's laws, you get to make a lot of decisions. And there's none of them that are really wrong as long as you stick with whatever you decide. So we're going to start with a very simple form of a Kirchhoff's law problem. And then in the supplementary video that I'm going to do, I'll do some that are more complicated. Okay, so we're going to start with problem 7, part A. So problem 7A says, what is the magnitude and direction of the current in the 18 ohm resistor in the figure? So let me draw it. Now, you're like, well, this doesn't look too bad. It's just one loop and there's only one resistor. The problem is here is there's 2 batteries. And that's where Kirchhoff's law comes in handy because I can't reduce things down if there's a battery in the way. Okay, so there's 2 batteries. This one is 3 volts. I'm going to call that one V1. And this one is 6 volts. I'm going to call that one V2. And then this is 18 ohms, and I'm going to call that R1. Okay. Now, there are no junctions here. So the junction rule is not going to be something that I can use, but there is a loop. There is a loop here. If you look at this whole thing is a loop. All right. So if I look at this, there's one way to trace around this circuit, and it's just that, right? Or you could go the other way if you wanted to, but that's one loop. Okay. So I'm going to erase that so it's not in my way. But what I have to do is every unique branch gets its own current. Now, since there's only one loop here, we only have one current because there's nowhere else for it to go. Now, the trick to doing Kirchhoff is you have to decide a couple of things. I need to decide, unless they tell me, because in some problems they'll tell me, but they don't always. I need to decide which way the current's going to flow. So I'm going to guess that the current is going to flow this direction around the circuit, like that. I'm going to say it's going to go, what is that, counterclockwise. And I'm just going to call that I1. Now, I don't know if that's right or not, but here's the nice thing about it. If I get it wrong, I'll just get a negative number, which means my current's flow in the opposite direction. And as long as I stick with my directions, I'm okay. So even if you guess the wrong direction, you're still okay when it comes to doing the math for your problems. Okay, so don't get all worried about, oh, did I pick it the right way or all that. It doesn't matter. All right, so what the loop rule says is I can work my way around a loop, and as long as I start and end start and end in the same place, then all the voltages add up to 0. Okay, so the first thing I'm going to do is I'm just going to label my batteries here. Okay, then I'm going to pick a place to start. So I'm going to start going around adding up my voltages, and I'm going to start in the upper left-hand corner. Why do I start there? That's what I felt like doing today. And I'm going to go around this loop also counterclockwise because that's what I felt like doing. Could you start somewhere else? Yes. Could you go around the other direction? Yes. Your signs will be different than mine, but that's okay because they're still going to add up to 0. So you can't do this part wrong as long as you start and end in the same place. So for the loop rule, I'm going to start in the upper left-hand corner. Okay, I'm going to come down, and the first thing I'm going to do is I'm going to run into this 3-volt battery. I come in on the positive side, so I'm traversing the loop this direction. Okay, I come in on the positive side, I go out on the negative side, so that means that's a minus V1 because I go out on the negative side, so I'm losing voltage. Then I'm going to come here. Nothing's going on that side, so I'm going to turn the corner and go up. Okay, I come into this 6-volt battery on the negative side, and I go out on the positive side, so that's a plus V2, and it's plus because I go out on the positive side. Then I'm going to turn the corner, and I'm going to go through my resistor. Now, if you read the notes or watched the video, which I hope you did, if you go through a resistor with the current flow, that is a negative. You lose voltage. Since it's a resistor, I use Ohm's law. So I use I1 times R1. That's Ohm's law. Okay, so that's voltage for resistor. It's I times R. It's negative in this case because I'm traveling around the loop and going through the resistor with the current flow. So that's a minus. And then I'm back to where I started. So that means all those have to add up to 0. Okay, so I'm going to put in my number. So I've got minus 3 volts plus 6 volts minus I1, which I don't know yet, times 18 ohms. Oops. Okay, equals 0. So if I do some math here, I've got 3 volts left there minus I1 times 18. I'm going to rearrange this to solve for I. So if I do that, I get I1 equals 3 volts divided by 18 ohms, which is 1/6 amps. So it's 1/6, whatever 1/6 is if you divide it out. 1.67 amps. Now, Because I got a positive number, that tells me that I picked my current flow in the right direction. If I had got a negative number, instead of flowing the direction I've got it drawn up there with that blue line, it would be flowing the opposite direction. But in this question, it asks me magnitude and direction of the current in the 18 ohm resistor. So I would say it was 1.67 amps to the left. Okay, to the left. All right, so that's the power of Kirchhoff's laws. Now, they get a lot more complicated than that, but since we're out of time pretty much, I don't want to start another one. I am going to do a supplementary video for you where you can watch more of these. And so I'm not going to keep working on them, but I really want you to watch that supplementary video because it'll have more complicated ones and it'll go through them in more detail. And the way you get good at these is you see more examples. So I'm going to stop the recording.